Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is grid beauty. In this question, we're given a grid of size n into m, which contains all the integers from 1 to n into m exactly once. Now the grid is represented as a of I comma j, where I is in between 1 and n and j is in between 1 and m, where I denotes the row index and j denotes the column index. Now we define the beauty of the grid as the maximum integer x, such that the whole grid can be sorted. Now what do we mean by sorted? So we'll just simply write all of these as 1, 2, 3, 5 dot 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 till m, then m plus 1, m plus 2, dot 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 till 2m, then 2m plus 1, 2m plus 2, dot 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 till 2m till 3m, and so on up till nm. Now to sort the grid, we can apply this operation any number of times. So we can choose some integer x and swap the positions ij and kl if the following condition is satisfied. Now, what is this condition? The condition is the difference in the rows, that is I minus k, the row numbers, plus 1 into the difference in the column numbers, that is j minus l plus 1, is greater than or equal to x. This product is greater than or equal to x. And if it is true, we can swap these two elements. Now, it can be proved that it is always possible to choose some x such that the grid can be sorted using the operations. Now, we need to figure out the maximum integer x such that we can sort the grid. Now, just to understand this operation, swap operation better, let's say we are given these two grids. This is the sorted grid. So if n is 4 and m is 3, this is how our final grid should look like. And let's say x is equal to 2 and we're trying to solve these two elements. The row number and the column number of this is 2 comma 1, and for this it is 4 comma 3. Now what is this value for it? It is 2 minus 4, that is 2 plus 1 3, into what was the other value? 1 minus 3 2. So 2 plus 1 3. I think 3 into 3, which would be 9 only, which is easily greater than or equal to 2. So we can swap those two elements if x is equal to 2. Now we're also given that it is always possible to choose some x. So if we choose some x equal to 1, it is always possible, right? Because even if let's say we choose 1 comma 1 and the other element is also 1 comma 1, then 1 minus 1 0 plus 1 is 1, and if you multiply it with the 1 minus 1 plus 1 1, it is still greater than or equal to 1, right? So if we choose x equal to 1, then we can swap any two elements, and because we can swap any two elements, it's always possible to sort the grid. Now, the prerequisites for this question are connected components. You should know how to calculate connected components using any of the methods like DFS, BFS, or the DSU. And you'll also need to know what my research on answers is. For the constraints, we're given that the test cases will lie in between 1 and 10 raised to the 4, and n comma m would lie in between 1 and 2 into 10 raised to the 5. We're also given that the sum of n into m over all the test cases would not exceed 2 into 10 raised to the 5. And all the elements of the grid would be distinct from 1 to n into m exactly once, right? Now let us see a few sample inputs. So in the first input, we're given just this one. So the maximum x, like this is already sorted, right? So the maximum x that we can get is like n into m plus 1, which is 1 into 1 plus 1, which is 2, which is the answer. For this also, the grid is already sorted. So the maximum answer is 2 into 2 plus 1, which is. Now for the third input, we can swap these two elements. And in that case, like we need to swap these two elements. And if we are swapping them, then like this would be the cost, which would be the value of our like this thing, and this needs to be greater than or equal to x. So the minimum value of x needs to be like the maximum value of x needs to be like 4, right? So if I'm swapping them up, it cannot be more than 4. So this would be 2, this would be 3, and the overall grid is sorted. So the minimum value of x, the maximum value of x that we can get is 4. And the fourth input, we have 1 cross 5 grid. Now what we can do is we can first of all swap this 4 and this 2, which will give us a cost of 3, and then we can swap this 1 and this 4, which is also a cost of 3. Then we can swap this 5, like this 5 and this 4, which will give us a cost of I think 4. And then we can swap them, which will also give us a cost of 4. We can swap them, which will give us a cost of 3, and we can swap them, which will give a cost of 5 or 6 or something of that sort. So the minimum, like the maximum value of x that we can get is going to be equal to 3, right? So yeah, this is pretty much the sample inputs. Now let's move to the solution. So first of all, we are given that this condition must be true, right? So if this condition is true for some value of x, for some x this is true and we're able to like sort the whole grid by some x, then can we also always sort it with x minus 1? We can, right? Because if this value is greater than or equal to x, it will obviously be greater than or equal to x minus 1 as well. And we can just apply the exact same swaps that we did using this value of x, and we can still like sort the whole grid, right? So the possible values of x would look something like it is possible for this, then possible, then possible, then possible, up till some value, which would be our x, and then it is not possible for all the further values, right? And because it is a monotonic function, we can apply binary search, right? So now let's try to figure out that, like, if we can sort the grid, if we're given some value of x or not, right? So let's first of all think of it in terms of graphs. So let's say we have some nodes. So let us consider all of these elements as nodes. Now let us say we have some ij and kl, and if for this ij and kl, if this condition is already satisfied, we can add an edge in between them, right? So if these two satisfy the condition, add an edge. If these two satisfy, add an edge. If these two satisfy, add an edge, right? And this way, what would this represent? All the elements or all the nodes that are connected in a graph by some edge are swappable, right? So if this node, this node, this node, this node, this node, this node, and this node, if all of them are connected by some edge, that means we can swap them in whatever order, in whatever way we want, right? And if all the elements which needs to be placed at these locations are present at these locations, then we can like sort that grid, right? So if the number we want to place at I comma j, so if there is some number we want to place at I comma j, so for example, for here the number we want to place would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number we want to place at this location is 9, right? So if this 9 and the number which is already present at this position belongs to the same component, right? Same connected component, then we can sort the grid if this is true for all the values of I comma j, right? So like the number which needs to be placed here and the number which is already here are in the same component. We can swap them up, and if that is true for all I comma j's, then we can sort the grid, right? So this is one possible solution. Now, what would be the time complexity of this solution? It would be there would be n into m square edges, right? Nm square whole square edges, because we would be comparing all of the pairs, and in the worst case, there could be up to nm square edges, and there are nm nodes. Now, what would be the time complexity of finding all the connected components, or like calculating if two nodes belong to the same component? Nm whole square plus nm, right? Now, what would be the total time complexity if we include the binary search as well? Nm whole square plus into nm, right? Which would obviously TLE. So we need to optimize this, right? Now our idea is, do we really need all the edges to check if two nodes belong to the same connected component? Right? Do we like for some node, do we need to compare it with all the other nodes to check if this and the node required belongs to the same component or not? Or can we like just optimize it? So let us say that this is one node and this is some other node, and they are already connected by some edge, right? This is some edge which they are connected by, or like we can connect them with this edge. So if we can connect these two nodes, right? Can we connect these two as well? We can, right? And if we can connect these two nodes, can we connect these two as well? And if we can connect these two, can we connect these two as well? Right. So instead of checking this with this, can we simply connect them up if they can be connected, connect them up if they can be connected, and connect them up if they can be connected? And if all of them are connected, that means they belong to the same component, right? So what I essentially mean is if these two can be connected, then this, and this can also be connected. So instead of finding the pairs, like connecting it with all of them, or like checking it with all of them, we can simply check it with four possible values: this, and this. And similarly, for this node also, we can just check these four values, this, and this. And after connecting them, if these two belong to the same component, then we are good to go, right? That means this can also exist. Similarly, if let's say we have something like this, if these two can be connected, we can say that these two can be connected. Oh, sorry, these two can be connected. And if these two can be connected, then these two can also be connected. And these two can also be connected, right? So instead of checking this with all of the nodes, we can just check this with this. And similarly, we can check this with this, and this, these four nodes only. And we are pretty good to go, right? So how many edges do we have now? For each of the node, we are just calculating four more edges, right? So now the time complexity is 4 into n into m, right? And the number of nodes are still nm. Now what would be the total time complexity? 4nm log nm, which is nothing but nm log nm, which would easily pass in the given constraints. And that's pretty much the whole solution as well. So now let us see the codes in C++ and Python. So we'll begin by taking in the input of the whole grid. This is our checker function, and here is our binary search logic. So we have initialized I with 1 and j with n into m plus 1, and our answer initially is minus 1. Now, if this middle value is correct, we'll increase our I and set our answer to mid. Otherwise, we'll do this and print our answer. Now, let's see the check function. So we have four possible corners, right? So, by the way, there is zero-based indexing everywhere. So instead of 1, 1, there is 0, 0. Instead of 1, m, there is 0, m minus 1, and so on. So these are the four corners which I need to connect every node with, if possible. So we'll run a loop for all the nodes. Then we'll run a loop to connect this I comma j node with this corner. So this is the distance. Now if this distance, like this is pretty much a distance formula which is given in the question. And if this distance is greater than or equal to x, we'll connect these two nodes. Now what is the node present here? Yeah, we'll just simply connect those two nodes. So this is like I into m plus j, and this is corner of 0 into m plus corner of 1. So this is basically just to convert the pair into a single number. So basically, like essentially what we are doing here is mapping the numbers like this. So we'll call this as node 0, 1, 2, 3, 4, 5, 6. Then this is 7, 8, 9, 10. So 1 comma 1 would be considered as 0, 1 comma 2 would be considered as 2, sorry 1, 1 comma 3 would be considered as 2, and that's it. So we're simply just mapping these pair of integers into single integers so that we can give them to a DSA function like DSU. Or alternatively, you could just like define this DSA for pairs of int comma int instead of just integers, and that would also work. Now here is our checking logic. So if for each node, the value at that place and the node which needs to be present there, if they belong to the same component, then we are good to go. If they belong to different components, we'll return false, that it is not possible to sort the grid given this value of x. And otherwise, we'll return true. Right. And that's pretty much the whole solution. The time complexity is n into m log of nm, because this is nm and this binary search will add log of nm component to it. Now let's see the solution in Python. So we'll begin by taking in the input of our grid. Then over here, this is our check function. We'll begin by taking in the input of the whole grid. We'll define a binary search. So our low is 1 and high is n into m plus 1, while low is less than high, mid is this. And if check is valid, we'll set low to mid, otherwise we'll set high to mid minus 1. And in the end, we'll simply print low. And here our simple DFS union find structure. Now let's see the check function, which is the most important. So we'll define our n and m. We'll define a DSU. So over here, we are just running over each of the nodes, and we're trying to connect each of these nodes to the four corners. So these are the four corners in the zero-based indexing. Now we're calculating the distance of the node ij with the corner, and if that distance is greater than or equal to x, we'll simply connect these two nodes. Which two nodes? I comma j, and whatever value is there in the corner. Now, why are we like calculating it like this? So essentially what we're doing here is mapping the pair of integer into a single integer. So how are we basically mapping? So we're mapping them, like if it is 1, 1, we're mapping it with 0. If it is 1, 2, we're mapping with 1. And we're simply like mapping it like this. So if the node is 2, comma 4, we're mapping it with 10. And we're just doing it so that because like the DSU takes in the union of integers, we could also define the DSU to take in pairs and all, but you could try that out, but it's not really needed. Now we'll check if it is possible. So over here, what we are doing is we are running over each node. Now, if the value that needs to be placed here, which is I into j plus I into m plus j, and the value that is present at this node, if they belong to the same component, then that is fine. But if they do not belong to the same component, we'll return false. And in the end, we'll return true if for all the nodes, they belong to the same component. And yeah, that's pretty much the whole solution. The time complexity is nm into log of nm because this check function takes n into m time. And this binary search will add a component of log of nm. And yeah, that's it for this video. I hope you liked it. Thanks. Bye.